In this video, we're going to cover some information that you will need when you begin to study polynomials. So it's some background information, but it's based a lot on some things that we already know. So we'll start by talking about exponents. Let's cover the basics. So here's an example. This is an exponential form, 3 to the power of 4, you could say, or 3 to the 4th power. We want to, first, let's cover the terminology. So the little guy, the 4 in this case, is what we would call the exponent. The number 3 is the base. And this exponential expression tells us it's 3 times 3 times 3 times 3. It's always the base that is the number that gets multiplied over and over again, and the exponent tells us how many times we see this base in the repeated multiplication. So we definitely think of exponents as a way to show repeated multiplication. I like to, when I'm talking about exponents, often look at this, what I'll call expanded form. It's not just me that calls it that, it's often called expanded form because I can really see the multiplication operations there, and it helps me understand what moves I can do and what would be not correct moves for the problems that we'll see very shortly. And finally, we know that we can actually do this multiplication when they are numbers. 3 times 3 is 9, 9 times 3, 27, and then 27 times 3 equals 81. So just a quick background so we've got a good common starting point for where we're going next. Okay, I have to go here just to refer to some basic rules, some properties that we will see put to use in these upcoming situations. And I don't need to stress you out with this associative property of multiplication, but just basically what that one means is we take some multiplication problem, for example, 2 times 3 times 5, and the associative helps me remember associate, so that I'm using parentheses to help group some numbers together. These are associated. 2 times 3 times 5, and the numbers in parentheses, the order of operations will tell us do that operation first. So the numbers associated in this way would mean 2 times 3 is 6, and then 6 times 5 equals 30. Now, if I take the same multiplication 2 times 3 times 5, but I associate it in a different way, I associate the 3 times 5, grouping those together, that would mean do this multiplication first. 3 times 5 is 15, and then 15 times 2, 30. Now, we got 30 on both sides of this equation, and that's this property, that we can group numbers as long as the only operations we have are multiplication, then we can really group these numbers however we want. We often like to state our rules using variables just to say it doesn't work just for this example, 2 times 3 times 5, but it does work for any number we choose in place of a and b and c. So our rule could say any random numbers a times b times c, you can put parentheses around the first pair, or you can put parentheses around the last pair, and they will always be equal. And it doesn't just mean that we can group them in this way, it means we can group them however we want, and the multiplication will always lead to the same result. Another property that we use is the commutative property, and this is one that we've probably encountered before we even heard this term, commutative property of multiplication. So take 2 times 5, and then take 5 times 2. They will both equal 10. That's this commutative, and I see commutative and I think commute, like you travel somewhere, you move around. So we can take numbers involved in a multiplication called factors, and we can put them in any order and always get the same result. What are your thoughts about if I had to say some rule about this using variables? A times b equals b times a. That's all that we're saying, is that numbers multiplied together, you can do it in any order and always get the same result. Okay, so that's enough background there. To bring that to some things that are close to what we are about to do, look at this multiplication. We've got numbers and variables all mixed together there, but we should see only multiplications, no additions, subtractions, no divisions, so we can use those rules. And the way we would use them would basically be we can multiply these numbers in any order that we want. So I'm going to find all these 2's, and I'll put those together at the front of this multiplication. 2 times 2 times 2, just putting them in this order that I want to do the multiplication. And I'll finish up with the numbers, pick that 5 next and put that down there times 5. And then I'll go for the x's. We usually do those variables in alphabetical order. So x's, then y's, then z's if we had those. Okay, 1, 2, 3, 4 x's. I'll just put x times x times x times x. And y times y down there. So I've rearranged into a way that's better for me to continue doing this multiplication. I'm going to multiply all these numbers together. 2 times 2, 4, 4 times 2, 8, and then 8 times 5, 40. What should I do with these 4 x's all multiplied together? Well, right now they're in expanded form. Let's put them into exponential form, x to the 4th. And we'll do the same with the variables y squared. The very last piece is just a little bit of cleanup when it comes to how we can write numbers multiplied by variables or variables multiplied by other variables. We just stick them all side by side, and we have to understand that when it's written this way, there is a multiplication right here. It's 40 times x to the 4th times y squared. These are all multiplied together, and even those exponents, we know those are all multiplications also. So a very long list of factors. We did some rearranging, which we can do because there was only multiplication, and we put them into a nice order, and it looks simple. Now in this example, we did look at a lot of these factors in expanded form, and we will continue to do that for a little bit, but there are also some pretty useful, they're not rules, but situations that will help us go through some of these future problems in a quicker way. So let's get to some of these newer examples. Here we have 2 to the 3rd times 2 to the 5th power. And let's first look at these in expanded form. 2 to the 3rd, 2 times 2 times 2. 2 to the 5th, 2 times 2 times 2 times 2 times 2. It's a good thing I didn't make that 2 to the 10th. And between these two, there is also a multiplication. Okay? Now, can we use one of those rules? Can we say, well, it's all multiplication, so the parentheses, we can move those around. What I've done here is just I've lost the parentheses altogether, but technically this is placing parentheses around the very beginning and the very end. Now, it's not exactly what we saw when we looked at that associative property of multiplication, but it is a result of that. That rule, if we looked at the patterns a little bit more, we'd be able to show that this is something you can do also. Basically, you can take the parentheses, move them, put them anywhere, lose them, just as long as we have only multiplications in this list. And that's what we have. Now, look at this nice long list of 2's, and let's take it from expanded form and put it back into exponential form. And it would be, well, we've got 3 there and 5 there, so a total of 8, 2 to the 8th. So this multiplication, we can say, equals 2 to the power of 8. You are maybe starting to see some pattern that we could use based on what the exponents tell us. And I want you to definitely keep going with that idea, but I want to take this opportunity to make a point. We have in this problem a multiplication. I see 2 to the 3rd times 2 to the 5th, but look at what we have for the answer. It's another 2. All we've really done is change our exponent. It's those exponents telling us how many 2's we have in the multiplication. But really focus on this so you don't make a mistake, a common mistake, that we see 2 times 2 and think a 4 needs to show up over here somewhere. This is really, if you think about it, something totally different than what we've experienced so far. I used to see a multiplication and some numbers, and I'd probably end up multiplying them, and my answer should be 4 with some exponent, but that's absolutely incorrect. We have to see that these bases are the same. It's helpful if we even can see that these exponents show us just expanded multiplication. So 2 to the 3rd times 2 to the 5th is just telling me now I have 8 of these 2's in the multiplication. I've multiplied another list to it. 3 2's and then 5 2's, and now we've got 8 2's. So really be clear about this fact so that we don't kind of lose focus at some point and say, oh, well, 2 times 2, 4. It's a very common mistake that we should be working to avoid right away. Okay, so I said a lot about that. Let's look at another example. X to the 5th times x to the 4th. And our pattern that we maybe observed from that example with bases of 2, we should still see here. x to the 5th, so there's my x times x 5 times, and x to the 4th, x times itself for a total of 4 times. And again, they're being multiplied together. So this is really just one long list of multiplications. And how many times is x being multiplied? 9 times. Well, I should say there are 9 x's. So in exponential form, we have x to the 9th. So I hope you're beginning to see that what those exponents do, let's say just add them together to have this answer about how many total x's there are in this multiplication at the end. 5 x's times 4 more will give us a total of 9. Now let's try to say this one in a rule, okay? These letters A, M, N just stand for any old number. A, so that could be like 3 to the 5th. This is another A, so if that's 3, this one would have to be 3. This could be like 3 to the 5th times 3 to the 7th. But our rule says when the bases are the same, our answer also has that same base, okay? We're not trying to multiply A times A. We're saying keep that same base in the answer. And what did we do with those exponents? We added them. So we'll just put a little m plus n up there to say your exponent in your answer would just be what you get from adding together those exponents. And it only works if this is the same base down here. Okay? Let's talk about this a little bit more. Here's another example of how that rule could work. X to the 3rd times x to the 9th. We do have the same base. It's x and x, so our answer can have an x. And what should that exponent be? 3 plus 9, 12. Let's also look at an example or two of when this rule does not work. Here's an example, x to the 4th times y to the 5th. We should not be thinking add the 4 plus 5 equals 9, because this rule only is when our base is the same, when we're talking about lists of the same thing being multiplied over and over and over again. This would be x times x 4 times, but now over here would be 5y's, and we don't mix up x's and y's when we're multiplying. Really, if we saw this, the best we would do is just call it x to the 4th, y to the 5th. We know that there's a multiplication right there between the two, but when we're working with variables, we just place them side by side, and we understand that it means multiplication. Now, we are talking a lot about using this rule when we see the same base and not always writing things in expanded form. We will continue to use expanded form a little bit just to really show how these things work, and I think it will be helpful to always remember that it is how these rules are not, I don't like to call them rules because they're not brand new, they're just showing us how our old rules work in another way. It's useful to see things in expanded form. This helps me really understand why I can add those exponents together. I see 3 x's times 9 more x's. I have a total of 12 x's multiplied together. But in the future, we're going to use the rules to move more swiftly through some longer problems. Let's look at one more example where we cannot use this rule. We see an addition. And up till now, it's all been about multiplication only. Our rules were about if we only saw multiplication, no other operations. But it's a good place here for this type of a problem to show up, just to make sure that we really understand what we can and cannot do. What I think about when I see something like this, as soon as I see that addition, I think combine like terms. That's a good way to go. It helps me avoid making some bad mistakes. So I see an add and I think combine like terms, okay? Well, what do I know about this combine like terms? I can only put things together if they have the same variable or same base and the same exponent. So this rule about taking two different exponents and adding them together only works for multiplication. If it's addition, I have to think, well, these are just not like terms. They cannot be put together at all. I might, if I had a habit of writing things in descending order, I could call it x to the 9th plus x to the 3rd, but there really is no way to combine these two with addition. They're just not like terms, okay? So we see adds or subtracts, I think combine like terms. But if we see multiplication only, then we have some rules that we can put to use. And not, again, not rules, but some patterns that we know to be true. Now we need to look at a few more examples just to make sure we fully understand how these situations work. Let's look at this example, 5 to the 4th times 5. Let's look expanded form, 5 to the 4th, 5 times 5 times 5 times 5. And now we have another 5 multiplied in there, and it looks like we have 5 to the 5th power. Now if we know the answer is 5 to the 5th power, how does our addition rule work to get us to that kind of an answer? Well, we've got an exponent of 4 there, no exponent here. You might remember having seen this sometime in the past, that an exponent of 1 equals that same number. And now we see our rule work again, where if it's the same base, we can just add those exponents, 4 plus 1, 5. Okay? So when we see a number or a variable without an exponent, we know that it actually is a 1 there, always. And that sounds like something we can state using some variables. It sounds like another rule. A to the power of 1 equals. What would we want to write here to say, well, you can take anything to the power of 1, and it just equals whatever number that is that you started with. You could say A to the power of 1 equals A. We will see some situations in the future where we find some number, it just looks like a base with no exponent, and we will put a 1 there to show how all of our rules still work together perfectly. How about you try this example? Simplify, or you could say multiply, but let's basically apply what we know to these different things multiplied together and come up with some nice, small, simple-looking answer. Okay, so pause the video and try this, and when you have an answer, let's restart and look at the answer together. I need to observe that this is only multiplication, and also I've got all the same bases. These are all x to some power. What do I know about this x here? Well, I could say it has exponent of 1. And now our rule, it's often called the product rule. You know I have a problem calling these rules, but I just can't avoid it at times. Product rule, that's what it's often called, to say if you have the same base, your answer is going to have also that same base. Just add up all the exponents. So x to the 5th times 1 more would be x to the 6th. And then we have 2 more to make the 7th and the 8th. And our final answer, x to the 8th. Take another one here, and you can see that we have some mixed bases, x's and y's. Just try to apply the rule to the groups of the same kind of variable, if you get what I'm saying. Here's what I've come up with for an answer. Again, we have some variables with no exponents. We'll just throw in some 1s there, and if it's helpful, I do that. Anytime I see a variable with no exponent, I can put a 1. Now let's apply this product rule where if I find all the ones that have the same base, so x to the 3rd with an x squared, now I have 3 plus 2, a total of 5. And it's this one over here that makes the 6th. So careful there that we're not starting to multiply those exponents. And again, I'm with you that it's beginning to feel a little bit odd here. This is a multiplication problem. But what do we do to answer it? We just add the exponents. And it's a little bit of a hurdle that we have to overcome to just make sure that we're doing things accurately. And it's helpful for me that I always think back to that expanded form. There's 3 x's and then 2 more x's and 1 more x for that total 6 x's all multiplied together. Let's get to the y's. Hopefully we're seeing 1 y with 2 more y's for a total of 3. And different bases, so we cannot go further than this. We definitely don't want to have anything to the power of 9. The different bases have to just stay separate, and x to the 6th, y to the 3rd would be our answer for this example. I'd like to take this opportunity to look at a few more of these examples that don't fit the rule that we've just been talking about to see how we'll handle those. But before we even get to those, just a quick little piece of information. Now, I would call this x to the power of 2 times y to the power of 3, or x squared with an exponent of 2. That's the one that is often called squared, and exponent of 3 is often called cubed. So this might also be read as x squared times y cubed. And I know I'll just go back and forth between those without really being aware of that. But just so that we're all clear on that. Exponent of 2 we can call squared. Exponent of 3 we can call cubed. Power of 4 and 5, there are kind of names for those, but they're very rarely used, especially just when we're talking about this stuff. So those I would call power of 4, power of 5, or fourth power, fifth power, and so on. Okay, now we have talked about this situation a bit recently. We know that there's no way to combine those exponents when the variables are different. We would just place them side by side, lose that multiplication because it's always implied when we have variables side by side that they are multiplied together. Here's an example where we have numbers, but we have different bases. So again, we will not be able to combine those exponents, but what should we do in this case? Well, it kind of varies. Some folks would say, well, it's fine just the way it is, 3 squared times 4 cubed, but you might want to, and again, I think this will just depend on your instructor, whoever you're working for. I'm usually okay with numbers, just multiply them all out. And so I would suggest, well, 3 to the second power is 9, 4 to the third power is 64. Those multiplied together, 576. That's what I would do with this multiplication problem. But just to leave it as is, I think is 100% fine as well, unless it was come up with an actual number. Evaluate this. If it was evaluate, I'd have to say go for 576. How about this example? 2 to the third plus 2 to the fifth. We know that we cannot try to combine these exponents when it's addition. It's multiplication only. So what would we do in this situation? Well, again, I would, when they are numbers, evaluate. 2 to the third is 8. 2 to the fifth is 32, and then I'd go ahead and add those to equal 40. So just a quick recap of what I would recommend for these situations where we know we cannot use that product rule. What would I do? Well, if it's variables, we just jam them side by side. If they are numbers, then I just evaluate. Always use order of operations, so I do this exponent first, and then that exponent and multiply last. In this example, it would be do the exponents first and then add last. I hope you have a good grasp on what we've covered so far, but we've really only started to scratch the surface. So let's take things up one notch, and again, this will all be manageable. We're basing things on some things that we've already known and some very clear patterns that we can see. So let's look at this example, 3x squared times 5x cubed. We know that this 3x squared is telling us it's 3 times x squared. What do we know about this 5x cubed? That's 5 times x cubed. Now, do we have all multiplications in this list? We do. We have some parentheses in here, but we know as long as it's all multiplication, these parentheses can go. We can also begin to pick out some numbers and multiply them in whatever order we choose. We're going to pull out the 3 and the 5 out front. We'll multiply those numbers together, and then the x's will bring those together after the number. So the coefficient will come first, and then we'll have our variables after that. Can we do 3 times 5? Sure. 15. Just a quick one. Still, we're talking about everything all multiplied together. Multiplications here, multiplication there, and there. 3 times 5, 15. Let's use what we know about multiplying these exponential expressions that have the same base. 2x's times 3x's, we have a total of 5 of them. So this multiplication would give us 15x to the fifth. Not so bad. We will get to a point where we don't always write things in expanded form, but let's use the same rules. What is at work here? The rules that tell us that we can multiply these pieces in any order we want. So we will get to a place where we say, okay, I see the 3 and the 5. I'll multiply those coefficients. 3 times 5 is 15. And now I'll find x's. Every place that has a base of an x, there's 2 x's and 3 x's for a total of 5 x's. So it will be good to know why it works, and thinking about things in expanded form is a useful way to see how and why things work. But as we go through problems, we'll begin to do it this way. where we look at the coefficients, multiply those, and then one at a time we look at the variables and put those together. Okay, not so bad. This is doable. You're going to actually do it right now. So pause the video, give this one a try. Remember what we just talked about, that we can pull out those coefficients, multiply those together, and then one by one put those variables together into our answer. So pause the video and try, and then come back and we'll look at the answer together. Well, let's talk about what I see in this big, nasty problem. First of all, I need to look at the operations, that actually we do have all multiplication. I saw a minus or a negative here, but that's just telling us that our coefficient right here is a -2. We have all of these grouped in parentheses, so we know that there's multiplications there and there. So that is just a -2. We'll treat it as a number that we use when we multiply those coefficients together, but we definitely have a list of only multiplications. I will begin to do the multiplications in the order I like. Let's find these coefficients. 3 times -2 is -6, and -6 times 4, -24. The coefficients and number parts are done. Let's look for the x's. X squared, and here we have x. We know about that. It's x to the power of 1. So we've got 2 x's with one more 3 x's. And now x to the third here, 3 with this 3, we have a total of 6x to the 6th. Next, y's. Let's just go in alphabetical order. We have 1 y there. No other y's. We do know that's a y to the power of 1, and we can put it there. It would definitely not be wrong if we had a 1 there, but usually we don't see it. Just like in this problem, the x that has a power of 1, we didn't see it there. We had to put it there or just know that it's there. We won't usually see it in our answer either, but when we see that y, we'll know that technically there is. If we wanted to see an exponent, it would be an exponent of 1. Let's just wrap this one up. Z to the third, z squared, that's a total of 5 z's. And that's it. Everything's taken care of. We multiplied the coefficients, and then we counted up how many x's and y's and z's, and there's our answer. Let me give you one more for you to try, okay? Just a quicker one. Take a minute, pause the video, try this one, and then we'll look at the answer. So we see 8 times -2 is -16. X to the third, and now here's x to the fourth, x to the 7th, and we have 1y, bringing down 1y. There's our answer. Now something just came to mind that I do want to go back to refer to. Up here, if you had a question about x, is this really x to the 1 or is it x to the 3? When it comes to exponents, they really only work on exactly what they're touching. That 3 is right on the corner of the z, so it applies only to the z. If I wanted this 3 to be referring to or to be used on the z and the x, I'd need to have those in a set of parentheses there with the 3 outside, and we'll talk about that at length very shortly. But just to be clear, if you had a thought back when we started this problem that should be an x to the third, I'd say no, that 3 is really only on the z. The x has that 1. Okay, now let's hop back here and talk about one last detail before we make our next leap. If we saw this kind of a problem where we did have an exponent outside, so exponent outside of parentheses is a way that we say it applies to this x to the third and also to that 8. But when we start to get into our flow of doing these problems, because they can eventually get pretty big and lengthy, I want you to know right now that when we see a problem that has an exponent outside of parentheses, there is something that we need to do first. That needs to be handled in its own way. If we saw this problem and began to do 8 times -2, it would be incorrect. So I have you on notice right now that when we begin to see problems where there is an exponent outside of parentheses, that needs to be handled in its own way. And in fact, we're going to look at that right now.